Well, hello and welcome YouTube, Mr. Robinson back here with another brand new exciting video, all math-based of course, and as always, it's an honor and a privilege to be serving you here today, as it is every day here inside my virtual classroom. Step on inside, and I'm already small. I want to show you this straight up front, guys. I got exponential properties all throughout here, a couple radical properties as well, in the way that exponents mingle with radicals, as they are all really under the same tree, just like addition is with subtraction, and multiplication is with division. Now we got exponents, or powers, I should say, and radicals, but the properties within. I'm going to write out some of these ones. We're going to have to retain them. I might have to scroll back up to show you what they appear like and what we're doing with them. Very minor explanation, and I got 24 problems for us to do. Here's the thing. They can take a while, or they can be very brief. My students know I can do these rapid fast in my head sometimes, but to get an explanation for you, I gotta sometimes spell out which properties are being used. But the further we go down this list of problems to do, the faster I am going to start going. Once you've seen a property hit a couple times, you'll start to make sense of what it is that's happening. So maybe slowly to begin with, and then speeding it on up. All right, first property here says x to the 0 power. What this means when it comes to x, it doesn't have to be a variable, but it says some base, a non-zero base actually, raised to the 0 power, is always 1. Not going to get too deep into the y right now. My students should definitely know why it is 1 and know that it's not 0. Yeah, there's nothing we can raise to the 0 power to get. There's no power we can raise to get 0, I should say. All right, so now we have a property here where we have a power, a product raised to a power here, and what happens is, and the proper word is not distribute, but you are in a way distributing the m into the x and the y, as in x is being raised to the m power and y is being raised to the m power. And again, what I'm mentioning here is if you have any product ever raised to a power, every factor of the product raises to that power. If you have a quotient raised to a power where you're dividing two things, both parts of the quotient, numerator and denominator, also get raised to that power the same kind of way. In essence, any part of a product or quotient, anything that's multiplying and dividing all together raised to a power, that power can go to each and every one of those things. Not can, it does. But when do you choose to do it? It's up to you. These are simplification rules, by the way. We will be simplifying these radicals completely, which means ultimately no parentheses is going to be a portion of that. All right, x to the negative m power. Now, positive exponents, if you guys know what an exponent is, when I talk about like 2 to the 3rd power being 2 times 2 times 2, positive exponents kind of describe how many times you multiply your number, or how many of your number is multiplying to itself, I should say. Negative exponents, if I did 2 to the negative 3rd, that's really stating how many 2's are being divided. If I started from 1, I could divide by 2, divide by 2, divide by 2. 3 2's divided. That's also an equivalent of multiplying 2 in the denominator. Really what's happening is 2 is being cubed in the denominator. It's about how many times your number is being divided instead of multiplied. So a negative exponent is all about really multiplying in the denominator, or dividing. And then negative in the denominator, exponent-wise, means multiplying the numerator. It becomes a numerator value. And these are the equivalents I'm giving you here. We don't evaluate with negative exponents. We don't simplify with negative exponents. We get them positive, we work them out positive, and we do what we can from there. Ultimately, all expressions simplified need to have positive exponents only. And positive integer exponents. I'm going to get into the integer part later. Now, when you are... Let's break this one down a little bit. When you are raising something to a negative exponential power such as this, and it's a whole quantity, specifically in this case a fraction, let's look at this one bit at a time. And exercising this property here, this would be x to the negative m over y to the negative m. And I want to get you hooked into this feeling automatically right now what I'm going to do. I want to write its positive counterpart for you guys. Obviously, this property would be applied here. But when you have a negative exponent, what do? You put it in its other spot. This will go in the denominator, this will go in the numerator, and they'll turn positive. So this becomes y to the m over x to the m. Now the equivalent that I want to write for you guys outside of all this is, I probably should have told you don't write this down yet, because what I wanted to do is show you just the transformation if it was still in parentheses. The quantity flips. We end up taking its reciprocal. If this is equivalent to this, then this is equivalent to this. Got an itchy nose here. And so what I really want to show you was this, is that if you have some fraction raised to a negative exponent, you can flip the exponent, keep it quantified temporarily, flip it, and still raise to that exponent, but now the positive counterpart of it. So turning them positive does that. All right, G, if you multiply two bases that are the same, ultimately what you do is you add the exponents. That's not new for us. Anytime x squared times x cubed is x to the fifth. That's not new for us to do. What may be new is when you divide them. I don't know if it's new for you guys or not, but if multiplying bases results in adding exponents, then dividing bases results in subtracting exponents, x to the m minus n power, like that, Shree. I just want to remind you guys, because my students ask this all the time. Wait, so multiplying means addition? No, I'm not multiplying the exponents. I'm multiplying the bases. That results in adding exponents, because exponents describe how many times you're multiplying something. That's just how it works. Same with dividing. I'm not dividing the exponents. I'm dividing the bases. All right, raised to those exponents. Now, I'll say power raised to a power here. M isn't raised to the nth power, but x to the nth power is raised to the nth power here. And ultimately, that results in your exponents actually multiplying. Again, I think I'm too bogged down by this to get into the nitty-gritty as far as the practicality and why that is. I think it's something we've got to kind of trust and use. Just kind of have these properties in play, have them written, and use them so I don't have to keep going back to them all the time, unless I feel I should. Now, this doesn't say, like if x was like 3 and m was like 2 and n was like 5. This is not 3 and 2/5 or 3 times 2/5. This is exponents. This is saying like 3 to the 2/5 power, like this. So x to the m over n power, that equals the nth root of x to the m power, or you can also write it as the nth root of x to the m power, either or. They're both pretty much one the same. And when I say that, I mean that ordinarily when it comes to taking a radical for something, we're going to tend to take the root first to make the numbers smaller and then raise it to the power afterward. But either's equivalent to that. And this property K is a lot like property B here, because like I said, they're like radicals here. If you have a product raised to a power, what if you take the root of a product? You can also split it up into the product of two roots, like this, just like we did for the raising that product into power for each factor. And same with division. The C is going to be a lot like L right here, where we can take the root, the nth root, of both the numerator and the denominator. So radicals kind of work in that same way because they are exponents. They're fractional exponents. We just showed that right here. They are fractional exponents. All right, I'm going to dive right into this here. Simplify each completely. Now, when it comes to simplifying, guys, what you might have noticed in these things, and they don't always work out the way that we kind of need them to, but what you've noticed is some things turn into one. There are things that have parentheses where they're saying, eventually we don't want parentheses. Some things with negative exponents where we say, well, we want positive exponents. Some things that have two of the same variable or the same base of some sort, and we want just one of them, right? So you can see some equivalence of what we're doing for some of these things. And then these work in tandem for how we want to work them. I'll tell you what, I only want positive integer exponents though. So if you have a fraction exponent like this, that's not an integer. I want to be able to convert it in a form where maybe if you have to have an integer here, have an integer here. We'll get it in radical form so we can work them more with numbers when we need to. Just note that, and actually we're not doing radicals yet for the first 12 problems, no radicals whatsoever. After that, a bunch of them. So maybe ignore these bottom three for now. We'll get back to them, right? Okay, number one, 5x cubed y quantity squared. We have to simplify this guy right here, as we're going to do all of them. Simplification for us will mean no parentheses. No parentheses. Evaluate all of your numbers. So eventually, I'm going to tell you right now, we're going to get a 5 squared eventually. I'm not going to leave it as 5 squared. I must evaluate what 5 squared is. If you have more than one variable, if you have more than one of the same variable written out outside of radicals, get them together in some way. They'll be multiplied or divided. Find a way to add or subtract their exponents. Positive exponents, positive integer exponents for that matter. If there's a fraction, reduce that fraction. If there's a radical, which there won't be for the first 12, we'll simplify that. If there are, that might be it. Okay. I don't know. There are a bunch of other things that you can do and talk about, but that's, and write the radical instead of the fraction. I think I already said that. Okay. I already have hiccups. Let me pause for 1 second. All right. I held my breath for like 15 seconds. We'll see if things come through. All right. Number one here, 5x cubed y quantity squared. Let's take care of something. We have an inside portion that looks like it can't be further simplified. This is 5 times x cubed times y inside of the quantity. Now outside, this is all being squared, and this is where we want to take care of things. When I say it's all being squared, I mean we are squaring all of it. We are going to square the 5. We are going to square the x cubed. we are going to square the y. So if I can get a rewrite of this thing, 5 is being squared. X cubed is being squared. Y is being squared. And don't get ahead of yourselves right here. Well, you can, but some people ask, well, like, what do you do? Just wait, cool, chill. We'll take care of it. 5 squared is 25 right there. That one's taken care of. 5 times 5, right? Now, x cubed squared. Keep in mind, we're not doing 3 squared with this. We are squaring x cubed. We're doing x cubed times x cubed. Case in point, we're using this property right here. A power to a power. Ultimately, the exponents multiply. We're going to have some sort of x to the 3 times 2 power, x to the 6th right there. And then y is being squared. Nothing else to say on that. And this is as fully simplified as we can get there. That's it. So we got them out of parentheses. Only 2 properties were used here. One was the power of a product, and then one was the power to a power, or power of a power, however you want to put that. So we use 2 properties right there. All right, number 2. W to the negative first power over V to the 4th power. Now, before I continue, and my students already know what I'm going to say right here, there's more than one way to do any of these problems. And sometimes I'll show you, oh, you can do this or you can do this. For the sake of this problem, I might do both, of doing this or you can do this. What you saw last time, what I did was I actually took that 4 and I applied it to the, I took the 2 last time and I applied it to every part of the product. Just like here, you can take the 4 and apply it to every part of the fraction right here. So you can take W to the negative first to the 4th power divided by V to the 4th power. And that gives you, as you multiply these two, that's W to the negative 4th power divided by V to the positive 4th power. Now, we're not done. We are nearly done. These will not subtract or do anything because these are different bases, but you do have a negative exponent. We need to turn it positive, and that doesn't mean just turn it positive. We need to write this guy's positive equivalent, and the positive equivalent will come from the idea of if this is in the numerator, if you want to make it positive, put it in the denominator. You don't need to, well, there will be a 1 over, but that's because there's nothing else written up top. If I wanted to, what I'm going to do is I'm going to take this W to the negative 4th, I'm going to turn it into W to the 4th down here. Ultimately, you're still left with a 1 on top. Remember, anything, W to the negative 4th is 1 W to the negative 4th, right? The 1 doesn't go down. 1 is multiplying with W to the negative 4th. And furthermore, V doesn't go up. This is something that, even my students, they'll be the first to admit. Students do this a lot. Bringing something down doesn't necessarily mean something has to go up in place of it. V to the 4th is a V to the 4th in the denominator. Why should it move? It didn't have a negative exponent. It's positive. That's going to stay there. And it's going to multiply with W to the 4th power. Yes, positive W to the 4th power. On top is a 1. And we're good. We're satisfied there. It's all taken care of. That is fully simplified. Now, an alternative to this problem right here as we work it out is, it's not really an alternative, but just, what if we took care of the negative first? What if we did that negative portion first and said, okay, let's move this thing down here, that W, that'd become a W to the 1st, and it'd be 1 over V times W to the 1st power, all raised to the 4th power. So if you want to take care of the negative first, and then move it down there to begin with, that's fine. And then what do? You take the 4 and you raise all these things to the 4th power, including the 1. 1 to the 4th power, V to the 4th power, W to the 4th power. Listen, 1 to the 4th power is just 1s. That doesn't change. And then you get the V to the 4th, W to the 4th. So you can see there are 2 different ways to do that problem, at least to start it off, and you ultimately land in the same spot. That's not going to change. I'm not going to do 2 different ways for every problem, and sometimes you're going to see me do one way for one problem, one way for the other problem. It really can become very interchangeable. One thing you're going to see me say for sure a lot, with those negatives, turn it positive and move it down to its other spot. Number 3, f to the negative 6th power. Let's move it down to the denominator. It's going to turn positive. H to the negative 2nd power. Let's move it down, make it turn positive. So before I take care of G, because it's clustered right there, I just want to rewrite this for you. Now I currently have 3G on top, and down at the bottom, I have f to the 6th, G, and H squared. I haven't touched the G's yet. I could have. It's just, again, it got clustered. I'm dealing with the positive exponents, the negative exponents first, making them positive. All right, I have a G divided by G. Let's ignore properties for now. If I asked you what g divided by g is, I hope you could tell me that was 1. Any number, non-zero value divided by itself is 1. So these can, in effect, cancel. You're going to see what I'm going to do with some other instances of having a higher degree on top and a higher degree on bottom and what we're going to do. But ultimately, I got 3 on top and f to the 6th and h squared right there. And that's all that remains. Positive exponents. And everything else comes into play. Number 4. 6x to the 6th, y to the 6th times 6x, y to the negative 6th power. To keep in mind, to remind you, first of all, that's multiplication obviously in between right there. But everything here is multiplication, right? 6 is multiplying with x, to the 6th is multiplying with y to the 6th, is multiplying with 6, is multiplying with x, is multiplying with y to the negative 6. There's nothing here that is not multiplying. Nothing. The parentheses are really just a courtesy of showing a monomial times a monomial. I could write this as like 6 times x to the 6th times y to the 6th times 6 times x times y to the negative 6. And there's nothing wrong with this either. In fact, multiplication is commutative. What I'm going to do is multiply the 6's together. I'm going to get a 6 times 6 going. I'm going to get an x to the 6th times x going. And I'm going to get a y to the 6th times y to the negative 6 going. You can see there's so many different ways I'm doing problems, and it's to introduce you to the perception and concepts of what's going on here. You are not required to do what I'm doing. If you did what I do, you would have multiplied these immediately. I would have said, hey, what's 6 times 6? Boom. Instead, I'm giving you the idea of parentheses aren't needed there. A rewrite can be done. 6 times 6 is 36. I'm going to do that. X to the 6 times x. That's x to the first power. We're going to use the property where we add exponents because they are the same variable. Treat x's with other x's, add those. X to the 6 times x is x to the 7th. Y to the 6 times y to the negative 6. You have two options here. Number 1 is add these exponents. 6 plus negative 6 is 0, so you end up getting y to the 0. Y to the 0 would be 1, and then anything times 1 is just that thing, so I can just get rid of that. That's one version. An alternative version of this is the y to the negative 6th. I could move it down underneath this fraction, and I'd have a y to the 6th over y to the 6th, and y to the 6th over y to the 6th is also 1. Those would cancel, and it's just a 1, and it's gone. Either way, you get 36 x to the 7th right there. That's your final answer. The y's are gone. Y to the 0 power remained. Or you divided all the y's. That's one way to put it. Okay, number 5. A lot of multiplication again. The difference is you got to know order of operations, and it's that we got to deal with the exponent and the exponent before we start multiplying the rest of the stuff out. So if you recall what we did on number 1 when it came to something that was squared or raised to a power within a product, what we did was we squared each individual part. I think it's at this step that I'm going to start doing a little less work on that and say, well, if we square the 3, we're going to get 9. I don't have to write 3 squared to show you that. If we're going to square x, we will get x squared. And if we're going to square y cubed, you don't square the 3 in y cubed, right? You square y cubed. You'll get y to the 6th power because you have that 3 times 2 going. So there's that guy. Multiplied, and you don't need the parentheses, but I'm just going to use it. Multiplied with this, how 6 distributes into the x and the y. And you get x to the 6th times y to the 6th. And just like the last problem, guys, everything here is multiplying. I shouldn't necessarily have to write these all as like dot, 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 dot and stuff to show they're multiplying. Anything in here is multiplying with anything else in here, but how can we simplify them? First of all, parentheses won't be needed ultimately. There will be a 9. 9 times this stuff. X squared times x to the 6th. Well, 2 plus 6 is 8. Remember adding the exponents. 8x is total multiplying. Y to the 6th times y to the 6th is y to the 12th power, and that is the end result. So again, simplifying, guys. I shouldn't have any parentheses, all that good jazz. We'll work that out. Okay, number 6. We have a fraction this time with this stuff. Now, not that, again, I would never do it this way myself, but as far as working some side work here, I'm going to rewrite these things so that they're separate fractions multiplying together for you to really compartmentalize this problem, that you get each individual part. I have 18 over 12. I'm going to work those together. I have x over x squared. I'm going to work those together. I have y cubed over y to the negative 4th power. I'm going to work those together. Numbers with numbers, x's with x's, y's with y's, z's with z's, things like that. You don't intermingle some x with some y and do something with them together unless they're quantified and raised to some exponent together, in which case you apply it like this. But they're not. 18 over 12, you don't subtract them. You actually divide. You reduce this fraction. 18 can divide by 6. 12 can divide by 6. You'd be left with 3 over 2 for those two things. They both divide by 6. Now, x over x squared. Okay, let me show you the stage that you can do with the property and what I tend to do and what I'm going to be doing here on out after I show you what I do here. X is x to the first power. When you divide two variables of the same base, variable-wise, you subtract the exponents. So this would be x to the 1 minus 2 power, which is x to the negative first power. Now, you can bet that eventually we need to write that as 1 over x to the positive first power. So yes, this will eventually turn into 1 over x. Remember, x to the negative first in the numerator becomes x positive in the denominator. Now, how do I do that? What I do is a straight up division. It's the same idea. It's subtraction, but this helps me keep them positive immediately, helps me know immediately where it is, and I can work through this part of the problem without having to show extra steps. X the first over x squared actually means there's an x on top and 2x's multiplied on bottom. And when you divide with common factors, you can cancel any pairs of them like this. So look what happened here. I removed all 1x's on top and one of the x's on bottom, and I'm still left with 1 on bottom. So the way that I really do it is I say, let's remove this 1x on top, no more x's on top. Let's remove one of the x's on bottom, and we're just left with 1 down there. And that's what we have. Now this y business I'm going to do a little bit differently because this is a negative exponent. What I want to do is deal with that and make it a positive exponent, as you know that I like to do. So this is going to be times, I got a y cubed and y to the 4th multiplied right there. We still got to deal with that. And remember, these are in the numerator together. If anything, it's over 1, right? It's a numerator value. So what is all in the numerator now? I got 3 times 1, which is 3, times y cubed times y to the 4th. These exponents will add and we'll get y to the 7th. On bottom here, I got 2 times x times 1, which is 2x. When you simplify, we should only have one fraction in the end. And I'm not planning on splitting up these fractions later. But as far as me separating them to show you that I do numbers with numbers, x's with x's, things like that, we'll do that all within the fractions that we're playing with ultimately. Let me zoom in on these things just a little bit. There we go. All right, number 7. 8m cubed n over 2mn to the 4th all to the negative first power. Now we've had previous problems. I've even mentioned that any part of a fraction, of a quotient or product that is raised to an exponent when quantified means this can go to every single one of those things. And there's nothing inherently wrong with doing it, but I would recommend 2 other steps before that. Step 1, I don't want to deal with negative exponents any longer than I need to. If I did, everything would turn negative, and that's just, you're just going to flip things anyway. Let's deal with the property that's stated if you raise something to a negative power. We can turn that power positive if you just flip this whole thing. 2mn to the 4th divided by 8m cubed n. If we just flip it right now, that's good. And you know what happens when you raise something to the first power? It's just that thing again. So let me just rewrite it. Don't even need the parentheses anymore. 2mn to the 4th, plus I need to write it better, over 8m cubed n. Now, I'm not done, but I've taken care of any part of the quantity in parentheses and stuff. The other thing I was going to state, and this isn't the only way that you can do this problem, but it takes care of that part immediately. The other thing I was going to state that you're going to see me do sometimes, and I've kind of mentioned it already, but sometimes you want to simplify what's inside before you raise it to that power. And there's no problem with that -1 because I don't change anything in the numbers anyway. But when you simplify an inside first, I don't know, you made things neater before you put something into there to affect it. Well, give me 1 second. Dry mouth, guys. All right. So now we got to take care of this. Just like we took care of the last problem. Numbers with numbers, m's with m's, n's with n's. I have 2 over 8. I need to reduce that fraction. 2 divided by 8 reduces to 1/4. M divided by m cubed. See if you can follow along with what I did last time with the x's. I have 1 m up here. I have 3 m's down there. If I get rid of this 1 m up here, I have to get rid of an m down here, and I'm left with 2 of them. How many are down below? 2. I have m squared. No more m's on top. I have 4 n's on top, 1 n on bottom. If I remove the 1 n on bottom, I'll have 3, and 1 on top, I have 3 left up here. So now I have n cubed. And you don't have to write the 1 as your answer. If you saw an answer key, it definitely wouldn't be there. This is n cubed over 4m squared. Now, I already answered it, and it might make sense, but some people ask, Mr. Robinson, how do you know which one to remove all of? Well, you can't remove 4 n's up here if you can't remove 4 n's down there. So you remove as many as you can on the side that has less. If I have 50 n's here and 100 n's here, I'm going to remove 50 n's from here and 50 n's from here. You can only remove as many as you can remove, right? All right, number 8. Numbers with numbers, etc. Meanwhile, I have negative exponents. Let's deal with those. B to the negative second power will become B to the positive second power in the denominator. A to the negative fifth power will become A to the positive fifth power in the numerator. Meanwhile, I also have 6 over 4, which can reduce, if I divide those by 2, to 3 over 2. Now, A's move up. I have an A to the fifth that I want to put up here. Remember, it's now a positive 5 now that it's up here. And, by the way, it's multiplying by this A right here times that A. So I got to make sure to multiply those two. On bottom, I have 2 times, I got this B cubed, and times this newly found B squared right here. I didn't have this B squared before. Now I do. So, work A's with A's and B's with B's. 3 is on top. A to the fifth times A is A to the sixth. This is divided by 2 on bottom. B cubed times B squared is B to the fifth power. And that is going to be the end result. And hopefully you're recognizing at least some of the properties that have familiarized, things that we've done before. And you're also recognizing kind of what simplification looks like, that you know when you're done. Maybe you don't know if you did the math right, but you'll know when you're done. There's, hey, what else can I do here, you know? All right, number 9, 3x to the 0, y negative third power, or whatever, z all to the fifth power. First things first, guys, x to the 0 power is 1. And if I get rid of it, that's all good and great, because that just means 3 times, or 1 times whatever is just whatever's left. So just get rid of it now. It's not going to be involved anymore. Just that knowledge is nice. We can deal with that negative exponent if you want now. I think later still serves its purpose because it's not with any other y's here. Let's take that 5. We're going to do 3 to the fifth power. That is 243. I casually know that. Y to the negative third, all to the fifth power, is y to the negative 15th power. You multiply the negative 3 and the 5. And then z gets raised to the fifth power right there. So you can see I'm starting to go faster on a problem that's similar to what we did before. Now, I'm not done. I need a positive exponent right here. So this will become 243. Z to the fifth, as this moves down, right, we are going to be dividing by 15 powers of y right there. As it moves down and becomes the positive equivalent. Remember, negative exponents does not mean negative numbers. It has nothing to do with negative numbers, actually. 0, zilch. Just means division. And divide it we did. All right. Let's move forward here. We still have a lot of problems to go, guys. 15 more, in fact. But these next 3 still remain in the whole non-radical, non-rational bits. Well, rational here, but not in the exponent. All right, number 10 is a good example of what I stated before here when it comes to, before I take this 2 and say, I want to square x, and I want to square y, and I want to square 9, and x to the negative fourth, and 3. We can simplify this inside first to start with, dealing with the negative exponent that I really wish were just positive. And, just intermingling some things here. So I have x to the fourth up top. I have x up top. Maybe we can deal with y right now. Y divided by y cubed. Let's remove the y from here. Let's remove one of the y's from here, and you're left with y squared. So no more y on top. I have 9 on bottom, and I have y squared on bottom. And this whole thing is squared. Now, x to the fourth times x is x to the fifth. So this becomes x to the fifth divided by 9y squared. And this is all being squared. And yes, this is all being squared. We get to square x to the fifth, 9, and y squared. So x to the fifth squared is x to the 5 times 2 power. That's x to the 10th. 9 squared is 81. A lot of people are going to put 18 thinking how you multiplied exponents. You're just going to have to be careful with that. And y squared, look, whether you do 2 plus 2, 2 times 2, or 2 to the second power, it's y to the fourth power. But that's when you multiply those exponents, remember. And that is the simplified version of that. Number 11, 1 over 3a to the negative third power, all raised to the negative, so it's 3a to the third power, all raised to the negative fourth power. If you want to deal with that negative right now and make it positive, that means you get to flip this into 3a cubed over 1, which is really just 3a cubed, right? All raised to the positive fourth power here. So now we take that fourth power bit, and we don't just do it with a cubed. A lot of people are going to say 3 times 4, 3 times 4. You're not wrong, 3 times 4 happens, but that 4 does not just apply to a cubed. It's also, you're also going to be raising 3 to the fourth power. So remember, it's 3 to the fourth times a cubed to the fourth. And 3 to the fourth isn't 3 times 4, it's 3 to the fourth, that's 81. A cubed to the fourth, you do 3 times 4, and that's a to the 12th. So you get 81a to the 12th power. Number 12. 10n over 30n cubed, all raised to the negative second power. Once again, it seems to make more sense to take care, because if you put that negative 2 into this thing, you're going to be, no. So it's better to kind of leave it on the outside. You can flip everything and turn it positive if you'd like to. And then what you'll get is 30n cubed divided by 10n raised to the positive second power. I still might not want to square things yet, because if you can simplify that inside and make things smaller, look, would you rather square 30 or would you rather square whatever 30 divided by 10 is? Meaning take 30 divided by 10 first, which is 3. Would you rather square 30 or 3? My answer is I'd rather square 3. That being said, 30 divided by 10 is 3. And n cubed divided by n, let's remove the n down here, and let's remove one of them from up here, and you get n squared. So I got 3n squared here, all being squared. That's squared outside. And now we square the 3 and we square the n squared, and we get 9n to the fourth power. All right, those are the ones that don't use radicals or rationals. They're either positives, negatives, or zeros when it comes to exponents. Now we're going to be dealing with rational exponents, and keeping in mind the general property, I think I got to write it for you guys, that this converts to this form right here, radical form. And the first 6 problems, I'm not actually going to use variables. We're just going to evaluate these numbers the way that they are kind of deemed to go. That doesn't mean other exponents, or other properties don't fly in the way, such as the negative exponent. We've seen several problems that negative exponents in succession, and this doesn't stop right here. So let's deal with that first. Negative exponent turns positive if I flip the quantity, 25/9 raised to the 1/2 power. Now I can take that 1/2 power, and I'm going to go ahead and do 25 to the 1/2 power and 9 to the 1/2 power, unless you want to convert it into its radical form right now. It's kind of your call here. If you want the radical form of this, keep in mind, guys, if I had some sort of, what I do right here, let's do that first. The x to the m over n equals the nth root of x to the m power. So the 2 down here represents the root for which we are going to be applying this radical. And 25/9, see, this is why I don't like to do this here. 25/9 is all raised to the first power, which really is just a fancy way of saying the square root, right? We don't write it 2 when it's square root. The square root of 25/9. That's what we're doing here. And in order to do this, there's another property that we have there that says when you take a radical of a product or of a quotient, you take the radical of both parts, top and bottom, square root of 25 over square root of 9. And I wanted to convert them radical form because we know how to use these. We know how to do them here. 5/3. Now what you could have done alternatively was taken the 1/2 right here, and you would have gotten 25 to the 1/2 power over 9 to the 1/2 power. And guess what? It brings you right back to here. 25 to the 1/2 is square root of 25. 9 to the 1/2 is the square root of 9. And then we're kind of done on that. Number 14. More of the same, only this radical, the rational exponent is now positive, so there's nothing to flip. We'll leave them as they are. And, I can go straight up into this one. I'll kind of do that opposite approach that I did last time. 16 to the 3/2 power divided by 81 to the 3/2 power. Now this doesn't mean you take 3/2 of 16, right? It doesn't equal 24. What you're going to do though is you're going to take the square root, that 2 would go here if we ever wrote it, of 16 cubed. But I'm going to cube last. I want to take the square root first. I don't know 16 cubed off the top of my head. I know the square root of 16 off the top of my head, and I might know that number cubed off the top of my head. Now here we get to take the square root of 81, and we also cube that value. Now the square root of 16 is 4. Let's cube that. And the square root of 81 is 9. Let's cube that. Not terribly small numbers here. The 4 cubed is 64. 9 cubed is 729. I just got a loud, annoying buzz in my ear, like a ringing. Like, my mom always complains to me about her tinnitus stuff now, and she says this buzzing in my ear won't stop. If I heard this all the time, I would go crazy. I hope this stops very, very soon. She always also tells me to not watch movies so loud, because I do that in my house all the time. Big home theater thing that I just do in my house. Hope this goes away soon. 121, I feel like I'm talking over it now. 121 to the 1/2 power. That converts to, once again, that's the square root of 121. The square root of 121 to the 1st power. Plus 125 to the 1/3 power, that's where you get the cube root of 125 to the 1st power there. The square root of 121 is 11. The cube root, I think it's going away. The cube root of 125 is 5. 11 plus 5 is 16. That one felt a little easier, and a couple of these problems may feel a little easier as well. Let's see if we can just mosey on through. For the 49 to the 3/2 power means the square root of 49 cubed. 64 to the 2/3 power means the cube root of 64 squared. The square root of 49 is 7. We are going to cube that. The cube root of 64, once again, is 4. We are going to square that. 7 cubed is 343. 4 squared is 16. 343 plus 16 is 359. Number 17. 9 to the 3/2 power means we're going to take the square root of 9 cubed. You might have noticed that I'm not writing those 2's. That's the implied value if it's not there. I need you to know that they're the same thing. I'm not just talking about my students. I just need people to know that. Minus the cube root of 8 squared. The square root of 9 is 3. We're going to cube that. The cube root of 8 is 2. We're going to square that. 3 cubed is not 9. 3 times 3 times 3 is 27. 2 squared is 4. And 27 minus 4 is 23. And before we dive into the variable ones here, we have this one here. 8 to the 0 power is 1. So kind of get rid of it because times 5. And so 5 times 16 to the 1/4 power. It's not 16 1/4 and it's not 16 times 1/4. It is 16, the 4th root of 16. What number times itself times itself times itself is 16? That is 2. So we got 5 times 2, which is 10. All right, those went by significantly faster. Now we're going to our last 6 problems here. So number 19. This is where we start dealing with things with radicals and rational exponents and things like that. Okay, so I don't know if it's going to show up. I think it does maybe in the last problem. But our final answer can only have positive integer exponents. That means only radicals ultimately in the end. That doesn't mean that right now I'm going to take x to the 1/2 power and turn it into the square root of x. No, in fact, as much as I loved using radicals for these guys right here, square roots, cube roots, and stuff like that, you really probably want to think of these in these forms here for several reasons. The main one is we can't take a square root of, if I ask you what's the square root of 9, you can say 3. If I ask you what's the square root of x, there's no answer to that because we don't know what x is. It's just whatever the square root of x is. So what we want to do instead is work with how the root version or its rational exponential portion can interact with other exponents in the properties that we're going to be playing with here together. So what I can do is take this x to the 1/2 and I can, I'm going to take this 4 and we are going to, apply it to the x to the 1/2 and to the y to the 1/4 right there. So we have x, I'm going to write this one out so you can see it in full. X to the 1/2 to the 4th times y to the 1/4 to the 4th. Now over here, we could do that equivalent. At least I can give you the written version of that. Keep in mind, when you take the cube root of this here, you're taking the cube root of kind of both of them, right? In fact, let me write the in-between step there. I'm going to put a few steps on this one since this is the first of its kind. You get to take the cube root of both of these as well, y cubed like that. Now, with this one, and I know that you know what's going on, but because it's a fraction, I want this to be a first-time thing. We're doing 1/2 times 4, which also means 4 divided by 2, as we'll get to that. And then this is y to the 1/4 times 4, which of course is 4 divided by 4. Now with these ones, if you prefer to rewrite them in their rational exponential counterpart right here, this will be x to the 6/3 power. See, now you know how these things work together here. And then y to the 3/3 power, like that. Now, you don't have to write it like this. What you do have to know is that these divide, 6 divided by 3. And 3 divided by 3. So I will often go without writing this version of this unless it's already provided that way, and it's going to interact with other things such as powers. Otherwise, I'll note that that 3 is the division for this thing right here. Now 1/2 times 4 is 2, so that's x squared. 1/4 times 4 is 1, so you get y. And over here, 6 divided by 3 is 2, so that's x squared, and 3 divided by 3 is 1, so you get y. So we got x squared y times x squared y, or really x squared times y times x squared times y, which does become x to the 4th times y squared. Okay, number 20. We can probably, at some point, these don't necessarily get harder. There's some parts that you have to rewrite, but we got the radicals involved. Let's live off what we just did on the previous problem to kind of make sense of how you can do a lot of these in very few steps. You have y to the 1/3 power all raised to the 6th. That means these two will multiply right here. 1/3 times 6 is 1/3 of 6. 6 divided by 3 is 2. So the top ends up just being y squared. On the bottom, I just made mention of this with like the 6 and the 3, and the 3 and the 3. That 15 will be dividing by that 5. You don't necessarily have to write that portion if you understand what 15 divided by 5 is, which is 3. Now we could be done, but we're not because we have a y dividing by another y, which means they can intermingle right here. I can remove all two y's on top and be left with 1. Remember, there is a 1. And on bottom, I'll remove 2 y's from the 3, and I just have 1 y down there. So this is going to become 1 divided by y, ultimately. That is the final reduction simplification of that one. Number 21, we have x to the 18th to the 1/3 power, and of course we will multiply the 18 with the 1/3, or 18 divided by 3, and we get 6, okay? And then we have the square root of x to the -8th power. Now remember, square root, if you don't see what's written, we're seeing squared, right? 2. You're going to be doing -8 divided by 2, and that's -4, so that becomes x to the -4th power. Now you may either add these immediately right here, or you can put it, say, in fraction form, x to the 6th over x to the 4th, as that goes down to become a positive exponent. And now we can do what I generally do, is remove all 4 on bottom, remove 4 from the top, and you're left with 2. Your ultimate simplification is x squared. Okay, I have 3 more problems for us to do. See if we can end maybe by the 15-minute mark. Maybe, maybe not. Number 22, we just did the square root of x to the -8th on the previous problem. Now we have x squared of x to the -10th here. You are dividing -10 by the invisible 2 that was, and that becomes x to the -5th power up top. On bottom, by the way, you can't do things with these yet, because this has a square root, this has a squared quantity. X to the -3rd is going to get it squared here, and that results in -3 times 2, multiplying right there, and that's x to the -6th. So not done with this thing here. I'm going to take this guy and move it down, and I'm going to take this guy and move it up as I change their signs. And I'm going to get x to the 6th over x to the 5th. And of course, we can then divide these things here. Remove all 5 x's from the bottom, remove 5 from the top, and you're left with just 1 x right there, or as I can just say, x. You know, you could use your division property here. That would be x to the negative 5 minus negative 6 power. Probably a lot of negatives for someone to work with, but you will get x to the first power from that. It's not like you won't. Okay, number 23. Again, multiple ways to look at it. Let's look at those multiple ways. One way is to maybe just work from the inside right here, and you can take 8 to these powers, which means, or to the whole thing, which means you're multiplying 8 by 2 and 8 by 4, and you'd get the fourth root of x to the 16th times y to the 32nd power. Then that fourth root says we're going to take each of these exponents right there and divide them by 4, right? So you'll end up getting x to the 4th times y to the 8th. So that ends up being the final answer. And that's one way of going about it. Alternatively, maybe you could have just worked with the 8 and the 4 to begin with. If you recall, this is a quantity right here. So the root of a quantity raised to a power is also equal to that quantity raised to the power divided by the root. 8 divided by 4, like that, which is, of course, 2. So you could have one version where you have x squared y to the 4th squared. And then you take that 2, of course, and you square the x squared, which is x to the 4th, and square the y to the 4th, which is y to the 8th. And lastly, number 24 here, we do have the square root of 1,000 times x to the 15th times y to the 20th. This time I'm going to separate them because I got to really focus on the numbers before I get any of the variable things. And this time we have something slightly different with the x variable. I'll show you what it is. Let's start with the square root of 1,000. Now, it's not a perfect square. It's not just a single number and boom. It is, the largest perfect square I can pull out is 100, and there's still a 10. The square root of 100 is 10, so I have 10 root 10 from the square root of 1,000. Now, x is a different story because, you know, as we talked about for exponents, of course, we divide by the root that's out here, in which case is 2. Y to the 20th, square root of y to the 20th is 20 divided by 2, which is y to the 10th. That one's fine. But x has a 15 divided by 2. And no, we're not going to start writing decimals like 7.5, 7.5, whatever. We are going to divide out as much as we can. And, you know, we did this over here as well with the 1,000. We factored out a perfect square of 100, which is 10 squared, and took its square root because you can take its square root. We want to find something that we can take the square root of inside x to the 15th. And the largest value you can is not x to the 9th, but x to the 14th. Because remember, you're not taking the square root of 14. You're dividing 14 by 2. Now, x to the 15th is x to the 14th times x. So I'm going to split this up into two things here, of which I can or know how to take their square roots. So the square root of x to the 14th is 14 divided by 2. There is 7. So you get x to the 7th. That root x stays inside the radical, just like this 10 did. We can't take its square root, so we won't try. And we have y to the 10th there. So ultimately, what you want to do, another simplification property is kind of just one radical, especially if they are the same root. So I have 10 x to the 7th times y to the 10th times the square root of 10x. Little more confusing looking in the final answer, but that's kind of what's going on there. All right, so that ought to do it for this one, guys. This is Mr. Robinson. I want to thank you so much. Is my eyebrow raising? I feel like, here we go, guys. That'll do it. My eyebrow's raised. That's weird. That'll do it for this one, guys. Mr. Robinson, thank you so much for watching these ones here. Note all the properties that we took care of. Kind of use them the way that I've been talking about them. Here. This is weird. Take care, guys. See ya.